Good day everyone, my name is Vidyasri Muniandi from Department of Mechanical Engineering. My metric number is 231111008. I am going to do presentation based on fluid mechanics. The code course of the subject is MMJ20103 and my lecturer name is Dr. Noor Saifullah bin Kamaruddin. There are two questions in the slides, so I'm going to explain question number 2a. A crane as shown in figure 4 is used to lower weights into the sea which have density of 1025 kg over meter cube for an underwater construction project. The dimension of the rectangular block is 0.4 meter times 0.4 meter times 3 meter and the density of concrete block is to be 2300 kg over meter cube. Both of buoyant force of the air and the weight of rope are negligible. For the question 2ai is determine the tension in the rope of the crane when the concrete block is suspended in the air. For the question number 2ai is consequently determine the tension in the rope when the concrete block is completely immersed in water. These are the figures for question number 2. The second slide is about the explanation of question number 2ai. First of all, we need to find the info. The density is about 1025 kg per meter cube. For the concrete is 2300 kg per meter cube. For the volume is 0.4 meter times 0.4 meter times 3 meter equals to 0.48 meter cube. Determine the tension in the rope of the crane when the concrete block is suspended in the air. P concrete lesser than density. Fluid velocity of air is W equals to P concrete times gravity times volume. 2300 kg per meter cube times 9.81 times 0.48 meter cube times bracket 1n equals to 1 Newton over 1000 kg meter square. The answer is 10.8 kN. For the question number 2ai is consequently determine the tension in the rope when the concrete block is completely immersed in water. Fluid velocity of water equals to W minus buoyant force equals to 10.8 kilonewton minus density times gravity times volume. So the answer would be calculated as 10.8 kilonewton minus 1025 kg per meter cube times 9.81 meter square times 0.48 meter cube times 1 Newton over 1000 kg meter square equals to 10.8 kN minus 4.8 kilonewton equals to 6 kN. Therefore, the tension in the rope when the concrete block is completely immersed in water is 6 kilonewton. The third slide is about question 2b. A 80 cm high aquarium with cross section of 2 meter times 0.6 meter that is partially filled with water as shown in figure 5. The aquarium is to be transported on the back of a truck. The truck accelerates from 0 to 90 km per hour in 10 seconds. Assume that acceleration remains constant and maintained in horizontal. Question number 2bi is if it is desired that no water spills during acceleration, analyze the allowable initial water height in the tank. For the BII is to minimize risk of water spill out from aquarium. Would you propose the tank to be aligned with the long side or short side parallel to the direction of motion? Justify your answer. This is the figure 5 for question number 2bi. Let's look about the answer. If it is desired that no water spills during acceleration, analyze the allowable initial water height in the tank. Ax equals to velocity over time equals to 90 minus 0 in bracket kilometer per hour over 10 seconds times in bracket 1 meters over 3.6 kilometer per hour equals to 2.5 meters square. For the tangent equals to Ax over gravity plus Az equals to 2.5 over 9.81 plus 0. The tangent would be, when we calculate, is 0.255. The acceleration of the truck Ax in bracket is calculated as 2.5 meters square. The analysis involves considering the forces acting on the water in the tank during acceleration. The formula tangent theta minus Ax divided by y plus Az equals to 2.5 divided by 9.81 plus 0 is used where y is the height of the water. Solving for tangent theta, the result is 0.255 equivalent to 72.44 cm when the short side is parallel to the direction of motion. The conclusion is drawn that the maximum vertical rise of the free surface occurs at the back of the tank, and the vertical midplane experiences no rise or drop during acceleration since it's a plane of symmetry. Therefore, the tank should be oriented with its short side parallel to the direction of motion to avoid spillage. Additionally, it suggests that emptying the tank such that its free surface level drops just 7.6 cm will be adequate to avoid spilling during acceleration. For the question number 2, BII is to minimize risk of water spill out from aquarium. Would you propose the tank to be aligned with the long side or short side parallel to the direction of motion? Justify your answer. The long side parallel to the direction of motion is elevation of point number 1 equals to b1 over 2 bracket times with tangent equals to 2 meter over 2 bracket times with 0.255 equals to 0.225 meter, also calculated as 20.5 centimeter. The short side parallel to the direction of motion for the elevation point number 2 is b2 over 2 in bracket times with tangent equals to 0.6 over 2 in bracket times with 0.255 equals to 0.076 meter and calculated as 7.6 centimeter. Comparing the two values, the vertical displacement elevation number 2 for the short side alignment is significantly smaller than that of the long side alignment. Therefore, to minimize the risk of water spillage, it is advisable to orient the tank with its short side parallel to the direction of motion. Thank you for your attention.